Hi, in this video we'll be talking about the problem knapsack revision. So this problem remained unsolved till the end of the contest. However, this was the second most hardest problem. So in this one, you are given n elements which are indistinguishable, and only the weights if the weights differ, the elements are different. Okay, and it's guaranteed the sum of the weights of all the elements is less than equal to 10 to the power 5. You need to find the number of ways to form a knapsack of total weight x using these items, and you need to find the answer for all the values from x equal to 1 to p. Okay, so the constraints are all 10 to the power 5. A modulo is dynamic, and modulo can be given up to 10 to the power 12, and it is guaranteed that the sum of weights of all is up to 10 to the power 5 only. Okay, so now a lot of people while solving this problem were trying to use FFT, but this problem is designed to not let FFT to pass, and hence the dynamic modulo up to 10 to the power 12, because if you want to get a FFT based solution of 10 to the power 12 for modulo 10 to the power 12, you need to have a precision of 10 to the power 24, 10 to the power kind of 24-ish precision, and that's not really easy with the normal long double as well. So things would overflow in between. Okay, so FFT won't pass in this problem. So this is not a FFT based problem. In fact, the next problem, the last one, magical revision, the magical notebook, was a FFT based problem. This is actually a DP problem. But before you go to the DP part of this problem, there is a observation that you need to understand, and then it's just a standard knapsack DP. So there is this line mentioned that it is guaranteed that the sum of weights is less than or equal to 10 to the power 5. Okay, so let's say there are 10 to the power 5 number of elements. Okay, but the sum of weights is up to 10 to the power 5. So how many distinct weights can there be in the array? How many distinct weights can there be in the array? Okay, so let's move to understanding this. So you are given summation of wi is less than or equal to 10 to the power 5, right? This is what is given. Now n is also less than or equal to 10 to the power 5. That's good. So with these setting, how many distinct weights are there? It turns out it is just less than or equal to something around 450. Like it will be less than or equal to around 400 or 500 or something. So this number of distinct would be order root n or root wi, I mean to say. Now why is that? Why is this the case? Why does it follow a root law? Because how can you create a worst case for distinct elements? Like there would be there would be an element with weight 1, there would be an element of weight 2, 3, so on, right? So you will try to create as many distinct weights as you can. So you will try to take the smallest one because that will not fill the weights first. But again, understand that as soon as you get to something around x, there would be less than equal to, and the sum has to be less than equal to 10 to the power 5. So this would be something like x into x plus 1 by 2 has to be less than equal to 10 to the power 5. Okay, so x has to be less than equal to something like 2 into 10 to the power 5, something of the order, something like this, right? So it turns out taking less than equal to 450 is sufficient for this case. Okay, so there are order, root and number of distinct elements. So now if we can somehow process the answers in for all these root n elements one by one, and then we can solve the answer, then we are done with the problem. So how do we solve this? So we use standard DP now. So now the problem changes into the balls are indistinguishable if their weights are same, right? So now the problem is you are given a ball of w1 weight. Let's take it as count 1 of w1 weight, count 2 of w2 weight, so on up to count x of wx, right? And the number of elements in this would be less than equal to something 450 for sure. Okay, so whatever this value is, obviously it would be less than that. Okay, So now these many elements are there. So now we will use the standard knapsack DP, but with a twist again. So how do we solve this problem with DP? That you're given the count and the weights of the elements, okay, and every element of the same weight are like indistinguishable, so just the count matters, okay. So let's try to understand how do we use DP in this case. Okay, so let's say we are trying to keep a DP. So DP of I is, and weight that you have seen till now is equal to DP of I minus 1 comma weight minus, let's first understand what this is. So weight minus some C, okay. So this would be the case sum over all C possible, okay. So what is this what we are writing? What is this transition that we are writing? So let's say this DP of I comma W mean the number of ways with the first I elements. Now what is this I element that I'm talking about now? It's that C1 W1, C2 W2. So this is our new problem, right? C3 W3, C4 W4, right? So this is our new problem, that so this I can be only up to 450 and this would be up to 10 to the power 5, okay. So C1 number of W1 weights are there, okay. So how many different ways can you create using first I of these, and you have created up to weight W. This is what we are storing in the DP, and for the transition part you can, like, the last element that you took, you can assume that you took C weights of the last element and the rest of them came from the I minus 1 states, right? So this is how you design the DP. Now if you're designing this C can only be finite values, right? So what are the values that C can take? So C will be allowed to take, C will be equal to either 0, that you don't take any of these, either you take WI, so you are considering ith element right now, right? So either you take ith WI 2 times WI dot up to CI times WI. Only these possible weights are that you can reduce, right? These are the only possible ways, because beyond that you don't have that many supply of CI. So if you think about it in this DP table, so this is the DP of I comma W that we are creating, okay. So for any particular cell, say this is your I, okay, and this is what particular W you are seeking right now. So this is the cell, okay. So this will either take from this, let's say CI is equal to 2, CI equal to 2 and WI is equal to 2 as well. WI is 2 as well, okay, sure, okay. So this cell will take either sum from this, okay, sorry, not up to this one, up to this, either from this or from this, like this cell. Why? Because either you don't take anything, you take one instance of 2, so this is the previous weight up to I minus 1, and then you took a 2 element size and you got to this one, or this that you had up to this much weight and this. So there can be some more elements in over here. So this is just a portion of the DP table that we are drawing over here, okay. So these are the 3 parts that it can come you can take the transition from, okay. So if now this DP's total array contains around 450 times 10 to the power 5 number of cells, right? So if for every cell now, if you loop over its CI values, if you loop over the number of CI cells, the number of count you have, so you will need these many transitions. So if you multiply it with CI, and which in worst case can be equal to the total number of elements, like only one particular instance has all the elements, so you need to loop over everything. So that will give you something like our 10 to the power like n square kind of complexity, and that will not be allowed. So you cannot do this transitions separately, so you cannot create this separately. So how do you solve knapsack problem where each instance has some number of occurrences? This is a very standard problem. but not a very easy one, because in the normal ones you have either infinite supply of items or you have just one instance of an item, right? In this case you have some ci number of items for each type, and how do you process them together? So that's not very trivial. So it turns out there is a way using some prefix sum, or you can even use DQ based techniques, but the the ideas go some things like this, that okay, let's remove this part. That let's say you are considering some particular cell, okay, so let's say this takes from this and this only, okay, let's say this and this only. Now let's say this will be the case when ci is equal to 1, right? This will be the case when ci is equal to 1, okay. So what we can do is that we know that only elements of two difference, like this element, let's use this element, this element, this element can contribute to these such positions, right? These, right? So any particular cell will have contributions from a two distant elements, right, from the previous row. So what we can do is that we can build a prefix sum on the previous row on the weight of the current row, okay. So I understand this is becoming complex, so let's understand it using a different example, just a single row with more values. Okay, so this should help. Okay, so let's suppose this is the previous row. So this is dp of I minus 1 and all weights are there, and this is dp of I, okay. And now we have, let's say we are considering this any cell, any of these cells, okay, and let's say wi is equal to 2 and ci is also equal to 2, okay. So now if we just quickly enumerate on things, like this would take contribution from this, this and this, okay, this would take contribution from this, this and this, okay. So for this element we need to quickly find the sum of these three elements, right? That's what we need. For this we need the sum of these three, for this we need the sum of these three elements, for this we will need sum of these three elements, okay. So if you see that this and this are quite overlapping, these two elements are same, just this gets removed and this gets added, right? So what is happening over here? You can build a prefix sum on this with a distance of 2, like this cell will store the sum of these two values of dp of I minus 1, this cell will contain the sum of these three values, this cell will contain the sum of these four values. So you are building a dp on these elements separately and a separate dp. Let's remove all these now. So we are creating a dp, prefix dp on these elements, and we are creating a separate dp on these elements, okay. So now this particular cell contains the sum of this, this and this, okay. This will contain the sum of this, this and all these, okay. So this is how we are building this dp, okay. So why are we doing it with two distance? Like why are we taking difference of twos over here? Because the weight is 2, because we know that every element over here takes contribution from like two distance element of the previous row, so that's why we are building it on 2, okay. So it depends on this wi over here. Now for any particular element you can find out its contribution by very simply taking the sum of dp of this, this and this. So this is ci, okay. So this would be some, so now after you have built this prefix sum in place, let's say we have built it in place in the array itself, so it will become nothing but dp of I minus 1 times whatever weight you are currently seeing. So this will be equal to, so this is what we are forming for dp of I comma w, okay. So this would be exactly be equal to this minus, let's understand what we subtract out of it. So this will be dp of I minus 1 comma, what is the weight that we subtract? So we can take 0 weight wi, 2 wi up to ci wi, right? So we subtract the part of w minus ci plus 1 times wi, because from there onwards all these multiples of things will not be included in that. Okay, so this is how we are building the prefix sum, and using that we will be able to get the sum of wi multiples in the previous row in the DP table. Okay, and with this in check we can get the values over here, and also obviously you need to check that whether this number exists or not, like whether this is in the array or not, or is it greater than equal to 0 or not. If it's not greater than equal to 0, you can just take this value to be 0. Okay, that's simply implementation level detail, but the whole idea is this, that for such like a knapsack where you have finite number of items for every type, you can build such a prefix sum on the previous row based on whatever wi is, and take these many sums from over here, because that's what the sum you really need. Okay, so if you build this prefix sum, now every cell's transition can be done in order 1, right? So in total you will need order root n times the summation of wi time to process all the queries. Okay, so this is the whole idea. Let me quickly revise on the whole thing. That first of all, there is an observation that you have only root n number of distinct elements that is possible, order root n number of distinct element possible. So we just first of all compress that up and just write down it as there are ci number of elements of weight wi, c2 number of weights of w2, so on. Okay, and next we try to build out this dp, that dp of I comma w, which is the number of ways in which you can form the weight w using the first I elements of this compressed form, that you have used c1 weight, c2 weight, so up to ci weight. Okay, how do you form this dp? So this you can form using the previous row and taking all possible weights, that is 0 wi, 2 wi, 3 wi, so on up to ci wi in this particular row. So this is a very standard knapsack dp, but this would TLE because you cannot do these many transitions. So how do you optimize on this one? You build a prefix sum on the previous row, but not a standard prefix sum, but a two distant prefix sum. Like you take only these sums. So this will depend on the wi value of the current row. Okay, so if it have been 3, you could have just changed this into this. Like you would have taken the prefix sum of these indexes together. You have built a prefix sum of this. So this will store this plus this. This will store this plus this, so on. This will be easy to build. Just a loop and add to the previous one. Just a normal one, but the bus that you are building over here, like a serial bus, but it's not like jumped. It's a jumped one. So you can add the proper indexes, and similarly this would be something like this, and there would be another one, this. So you can maintain these things, and then for every one of them you can just find out the sum very easily, like all 3 distant elements. So for every, in case this wi would have been 3, you would have needed for every element sum of this, sorry, not this one. Let's take this one, sum of this, right? So that you can find by taking the difference of this, that is sum of these, all these elements, these 4 elements, minus this part, which is the sum of just this one element. So this will give you the sum of these 3 elements, because this is how you build the prefix sum. Okay, so this is what we are doing over here, and then the transitions will be order 1, and in that case you will be able to create the whole array, and then at the final row of the array will give you the number of ways in each of them. So all these operations needs to be done in modulo. So since now we are writing a DP, the modulo doesn't, like, we don't depend on modulo to do any operation. It's just like addition and subtraction with some modulo, and everything is addition and subtraction. So we would be able to easily handle even modulo up to 10 to the power 12. Okay, so the final complexity would be order root n times summation of wi. Okay, so that's all for this problem. I hope you enjoyed this. Thank you.